when he was running another project, very, very ambitious and potentially game changer project of plasma filter to separate actinides from fission products, or light fission products from other stuff that could have revolutionized the nuclear fuel cycle. Unfortunately, I guess they ran out of money before realizing this idea. And then I got one day email from John saying that he's with Intellectual Ventures in Washington. And I thought
State of Washington, not the inefficient Washington.
And I was very busy at the time, so I thought it's a venture capital company.
Intellectual property.
Located in Washington, D.C. And it took me some time to realize that he is here in northern in Washington State, and pursuing
He kept flying to the wrong place.
advanced reactor concept. So I'm following TerraPower since 2007, about 7 years ago this time of the year. And it's amazing to see what John and how he managed to bring this idea that initially was very, very, in my view, not very practical, to something that everybody now in the nuclear engineering business wishes to be part of. So, and in addition to this amazing achievement, I think, I want to thank John and TerraPower for keeping supporting research, in our department for a number of years, with no string attached, to enable students to pursue.
There was a string attached. That was excellence.
Yeah.
And he had no problem with that.
Okay, so I didn't cover in the introduction the many positions, important positions that John had.
I'm going to cover that.
Throughout the years. He'll cover that. And John?
Okay.
Thank you for coming.
I did a bait and switch here because I said, well, I'll talk about global problems that need global solutions. I didn't quite know what that meant, but I thought that sounded like a nice title. And what I had in mind, of course, is to find an energy source that doesn't ruin the planet while we're implementing it. And I thought further over the weekend and decided, well, I'll rename the talk International Collaborations 101. My understanding is 101 is usually a beginning course. And some of the lessons I've learned. Eventually I'll get around to TerraPower, but I had understood that people before me had come through and talked about the traveling wave reactor and all that jazz, so I'll talk about that at the end. But I thought more and more the young people in this room would find themselves working on an international basis, because China's coal is burning as our problem, and carbon in the atmosphere is everybody's problem. We can argue about how much man is the cause of the climate change or not, but most opinion is there's a correlation there. And so I want to kind of work my way up to TerraPower and the tidal wave reactor, but that was born of a very rational process by Bill Gates in 2006. And so I'll come back to that. But I thought, for amusement, the young people who were not even born when I was doing some of these international collaborations could benefit a little bit by some very loose observations on what works and what doesn't. Because between electronic media and what my 6-year-old son said to me when we were working on ITER, we were toying with the idea of using something called an internet to communicate more efficiently, and we started arguing about where to keep the design. And my 6-year-old said, well, that's easy, Dad. It's up there in the internet. And he had this vision of a golden net around the world. That's where you put all the information. Way ahead, way ahead of me. So let me back up and talk about my collaboration list. And I'll say a few words about these today. And some of the young people here will be running programs, and they should call me up just before they implement some international thing, and I'll tell you all the things not to do. I won't be good at telling you what to do, but what not to do. I've been involved in collaborations with Japan. I say Japan and California, that's really General Atomics. ITER, everybody knows what that is, right? Okay. I was the U.S. Managing Director in that phase, and that involves all industrialized countries just about these days. And Archimedes that you just spoke about, we had programs with France and Russia to try to implement that technology, and then finally TerraPower and its traveling wave reactor, which is one version of I call it Generation 5 of reactor, but that's just my PR going. And that involves the USA, China, Russia, Japan, and UAE some now these days. And so I would like to talk about these one at a time, just for the sake of being a sort of a historian. And these, all of these, though, I'll make an initial observation for you, and that's, yes, having something technically good and important to do is necessary, but it's not at all sufficient. What triggers the activity usually has nothing to do with you and your technical beliefs. It has to do with some completely separate problem that political leaders are attempting to address, as an example. And so there was a collaboration between General Atomics and Japan, and that was done for what I'll call balance of payments amends, and I'll explain what that means. ITER was came out of the Reykjavik summit with Gorbachev and Reagan and Velikov sort of planning ideas, but it had more to do with needing to find ways to work together than any specific love of fusion. Archimedes, turns out some very generous people were worried about the environmental problems associated with Hanford and those tanks of waste up there, but this also had application in fuel cycle. And so Dan Evans, the ex-governor and senator from that place, and a bunch of generous investors in this area put a lot of money in, about $100 million in getting to where a full-scale prototype was built. But again, it's interesting that France and the CEA participated in some of the other French companies because they wanted to plant people in an environment to learn about the California way of doing venture things. And that motivated them just as much as anything to do with the technology. And then Russia at that time had just disintegrated, and the Russian scientists needed money. And there were a lot of great people, and we erred in that direction, and we got a lot out of it. And then the TWR and that sort of development program that you just mentioned, that came out of a very rational process, which I'll describe. So this is giving you a sense of where I'm going with these things. Now, how about what's called now the D3D Fusion program? That started as the DIIID program in 1972. I was a newly minted PhD at the time, fairly newly minted. And it is, for those that don't know, an advanced form of tokamak. So people know what a tokamak is, I imagine. And we were doing pretty well. We had got some DOE, or then whatever it was, EPRI or something, money. Not EPRI. But whatever the name was before DOE. And we knew what we wanted. We were busy starting to design and build the machine. But we also knew that after we got the machine built and tested, we wanted to have additional heating equipment. We wanted to have additional diagnostics. There were lots of things we wanted. And suddenly it was observed that in the newspapers that a contingent of Japanese executives was coming to the United States. And what they wanted to do is to make a big gesture to the United States because the balance of payments was just ridiculously favoring Japan at the time. And Congress was starting to make noises about trade barriers and so forth. So they decided we need to make a big visible gesture. So the CEOs and chairmen of some of the bigger industries in Japan came to the United States with the intent of making some big investment in research in the United States and make it quite visible and showing they're good guys and they understand it would be good for us, it would be good for them. And so they came and they went to national labs and they went to universities and they got these very warm responses like, of course we could accept your money. We'll get back to you in 6 months after we figure out what it is. Well, a good CEO, I learned from D3D Fusion, always has a play in mind in case someone comes around with a check. And so while D3D, who of course was a great Japanese and an American physicist, plasma physicist, while he was talking to them and giving them some general descriptions, because he already knew roughly how we could use a big investment of funds. Well, while he did that, I, in my maturity at that time, I was a 32-year-old or something, was cooking up the details of what this thing would be and handing notes into the meeting, because D3D knew they had to go back with an agreement, period. And they did. They finally got a document in their hands. They could go back and say, our mission was successful. And so be ready, is my, a good CEO knows how much his company is worth and what to notice at any given time. Well, in this case, as researchers, if you're running a program of research, know what it is you want next and be ready, because the opportunity won't come along when you plan for it. It'll come along in some unexpected way often. So the two teams shared experimental time on doublet 3 at first, doing experiments on this sort of non-circular shaped plasma that actually had 2 lobes and promised great high performance, but engineering difficulties. And so that it turned out to be a very good thing. We ended up with, in today's dollars, maybe an extra $1 billion to put into the program over the years. And there were some very interesting things that came out of it. One was because the two teams culturally were so different. One week this team would have the machine, the next week the other team would have the machine, and we'd scramble in between to adjust the machine parameters and get ready. But thinking is a learned process. It really is. You're born with a certain DNA and all that stuff, but as you learn to think, as you know, neurons get connected. Even guys of my age had a little bit of plasticity left, even if I practiced my golf swing over and over. Not much in that area. So it was enriched because these teams who had different experiments to do did them differently. It was very characteristic of what I found out later with ITER. And that's that the Japanese would build consensus on their 12-person team, and they'd go all the way to the end, see what happened, come all the way back and look at it and decide build consensus and go over here. The American team was, you get about 10% of the way here and see these beautiful flowers off on the right. We'd take a right angle turn and go over there and explore that, and it would drive the Japanese team nuts. And they were very good people, had a very good way of doing things, but so did we. It was very complimentary. If I had to do it over again, though, I would tend to mix the teams more. The Japanese view was because they had to give up a machine in Japan, they wanted to build a D-shaped plasma machine also. But as a consequence of our jumping into this deal, they didn't get to build it. But they wanted to maintain their identity and independence. But still, I think net, you'd be better off having two different leaders a Japanese one and an American for these two teams, but mix them otherwise. It's a much more rich process. So, and I can spend a lot of time over here talking about that. In the meantime, we, with the Japanese, sold first Okawa and then the government on changing this to a D-shaped configuration from this more thrilling but less practical thing. And so we ended up with what's called the D3D. And the Japanese put a lot of money in that, and it became a center for plasma physics and fusion research. And it's still going today. And I take no credit. I was involved up through the design and most of the construction of this modification to be the D, but I had nothing to do with running that program after that. I left it uneaten. And, but very fruitful. What happens is if you have a very strong centralized control of the project, so that the design, the fabrication, all that's done on a merit competitive basis, you can get from here to there. If you have, however, a system set up to accommodate others, to bring in their diagnostics, to bring in their new experiment, convince you this experiment ought to be done, and then you develop a hierarchy and a whole pool of supporters in the country and in Europe and other places, because they get to come try out their brand new diagnostic. And you foot part of the bill, and the government grant gives them more money as well. And it's just an all-around win for everybody. And so that worked very, very well. It was continued better than I could have done, I'm sure, by my successor, some of whom came from Livermore, and some who grew up from the ranks in GA. And that's amazingly enough now, a third of a century later, they're still doing experiments on it. That's the inside. I spent more hours than I wish to talk about inside such vessels leak detecting. And so this is the cartoon which we looked at initially when we were talking about having this D-shaped plasma rather than a circular plasma tokamak. In the early days, that was considered crazy, just like traveling wave reactors or some of your ideas. And then later on, they become of courses. And this became a kind of course, that's the right way to do it eventually. And here we were not burning deuterium and tritium, we're just DD or less. And we were testing out how diverters work and confinement and energy densities, what kind of betas you could get, and mainly plasma physics. But it turned out to be the workhorse in supplying data for this machine. And you'll notice the difference in scale. See, there I am. And then there's after I worked too hard. I mean, wow. See this person here?
Wow.
So is this one of those too big to fail things?
Yep. I think they succeed.
Too big to fail?
Too big to succeed.
Or succeed, whichever way you want to word it. But that's really a monumental thing. I once called it International Cathedral Building. But I want to be fair, they're really great people working on this. And they've had great ideas, they've made great progress, and I have nothing to do with the parts. I was an editor of the conceptual volume 1 design from 87 to 91, but after that I went to work for Bechtel and did renewables and advanced fission and stuff like that. But lots of very powerful minds working on this. But what can you say? Well, you can say that was quite a scale up. But let's think about ITER. ITER got started because people, I exaggerate a bit, make love not war, but ITER was the convenient vehicle for having increased collaboration with and interaction between what was in the Soviet Union and the United States. And lots of nations joined in after that, not in the conceptual phase so much, but when you went into the engineering phase, followed by the construction phase. And for those of you who know about these things, know they're building the thing in France right now. Now it was a great political event, and I think it was the first time that people got together and assessed that there was sufficient real theory and real data that you knew you could build something that would work. Now, defining what will work is different for the fission guys than the fusion guys. The fusion guys is, gee, we'll make a gigawatt of power now. Whether we can practically orient it and use it someday, I don't know yet, but let's make history. And so that was a great outcome. There was also what I'll call the times $4 dream, which means 4 times less. At that time, there were 4 parties, so if the cost was $4 billion, then each party would come up with 1 and spread it over several years, and it sounds like a good deal. And then the engineering phase in La Jolla, which was the ideal place on the planet to have an engineering team. Know anything about La Jolla. And now the construction phase. And my observation is, I hope this thing goes ahead, but it is very, very good people trying to fix or deal with a flawed funding and managerial construct. So when you do this, don't do it this way to start. Start right. And ITER started right in many, many ways, but I think when you decide to give contracts and coils or other things so that everybody gets to build one, I'm exaggerating the logic, but it's a little bit like that, and you don't have a fixed hard budget with the team that has total monetary control and integration control and all this mean stuff that the Bechtels of the world would do, then it's destined to have some difficulties, and these difficulties have to do with, harkening back to a description I had to some White House staff. The White House advisor and I told them, well, I think this isn't going to be $3.5 billion, it's going to be north of 10. I was wrong, it's north of 20, and still counting. So hopefully it's not the too big to fail category, but and they are doing a good job of starting it up, and they are trying, I think, to reconfigure and fix the sort of managerial funding paradigm here. So I wish them well, but there's some lessons in that. Well, how about Archimedes? You mentioned that. And this was a bunch of wealthy people wanting to solve the Hanford weapons waste problems. They didn't have in mind how DIIID would use it to separate the groups for fission fuel, fission reuse. But it's an insight in how to build a what looks like a centrifuge, but it's not really. It's a group separator. You have a crossed electric magnetic field, and you spin the thing like crazy, but if you do it the way people have thought of in the past, well, you end up with a very expensive, pretty mediocre centrifuge. But if you reverse the sign of the electric field and do all the physics right, you find there's a definitive cutoff. And anything above a certain AMU goes this way, and everything below it goes that way, so you can take the heavy stuff and put it over here, and all the light Hanford waste stuff over there. Or you do variations on fuel cycle with this as well. And so, as I mentioned before, this is international because these outfits got intrigued by it and entered in and participated and contributed. And the thing worked. I don't have a picture, but there's a full-size filter where the sodium goes one way, which is a lot of the Hanford waste, and the surrogates for uranium, et cetera, go the other way. But what this group did is then offer something very generous. They would raise the money, run the machine at Hanford, and the government would not have to pay unless it worked. What can be more generous than that? Well, the U.S. government's handicapped. It's full of good people who don't have the freedom to act efficiently. This paradigm is not known to them. So I advise them to pack it up and give the rights to GA, who is used to marketing the government, and they now have the rights here. So if you have brainstorms on that, go to GA. But again, once again, the motives didn't start out with someone being in love with something called a plasma filter. There was a problem, searching for a solution, and then people cooked up the solution. So now we come to TerraPower, and that's really interesting in the sense that there's a fellow sitting around writing checks for billions of dollars trying to help out folks. There are vaccines, there are agricultural practices, there's just a long list of things. But he had the correct perception that there were 1.5 to 2 billion people without sufficient availability of energy to lift themselves out of poverty. What happens when you have essentially no energy available to you? Well, you keep inventing new diseases. You're living in squalor and you're dying. You shouldn't. And so he said, well, I'll tell you what, let's take a look at various ways to get that energy to people. And so solar was thought about, wind, sequestration of whole CO2, biomass, nuclear fission, fusion, and it's not very well documented, but some very bright people in 2006 just went through them all without prejudice, and ended up with the conclusion that if you add the requirement, it's got to be very low carbon, then you end up with fission. Fusion is great, but fusion is a great scientific endeavor still. It's not something my grandchildren, I just visited my 3-day-old granddaughter. It won't make a difference to her life, but fission can. And so, with that conclusion, we talked a lot about what opportunities for improvement are there for fission-based power. For example, I was concerned at the time, this is now December of 2006, I was concerned about the proliferation of weapons. So how could you do away with the need for enrichment plants and or reprocessing plants around the world if you're going to deploy thousands of reactors around the world? So that was my requirement. Others said, well, inherent safety features. Others said, well, it's really the efficient use of the uranium resource, and other environmental issues associated with it. And finally, Bill Gates would say, yeah, and if you can't afford it, it's all just theory. It's got to be affordable, or it's good things for professors to dream about, but I don't know what to do with it. So we had this circle of desire. We started at a different point on the circle, but we did not give up on any of those. And our mandate was his mind was to find a way to do it with little or no technology development. Invention, fine. Great engineering, inspirational, fine, but technology development, I don't want that, because then I don't really know how to do it. And by my definition of technology development. And so we took a look finally at a version that Teller and Woods had worked on, the traveling wave reactor back in the mid-90s. People had thought about it before that too. And it looked brilliant and impractical. But we got very practical people involved and worked on the concept and found, much to our amazement, during 2007 that we didn't shoot down the idea, it still had promise. And so much promise that Bill Gates and Nathan Myhrvold, the founder of Intellectual Ventures, had a handshake. And they decided to just start work, as I say, sans lawyers, which means you got to start. If you waited for the lawyers, who knows when you get to start. But it turned out sometime in 2008, the lawyers finished and TerraPower formally existed. And we're sort of in the range of $1/3 of $1 billion now, expenditures, et cetera. Or at least will be there in a while. And I think one of the interesting things was that we we're able to go at our own pace. It's just a great gift that Bill and other like-minded investors, he's not the only one, there are others that put considerable money in. They pretty much said, we endorse your goals. There's the white blackboard. Gee, I said blackboard. These ones. Got to modernize this place. Anyway, and so we got the start, and as we started out with a lot of Livermore people who knew a whole lot about what sort of programs existed and how to adapt them to more practical things. And that was natural because Lowell was involved heavily. But then we brought in people from industry, other institutions, and slowly built up a more complete staff to really look at this, and found, much to our amazement, that there was an embodiment that could be carried out, that something would achieve these goals. Pretty much. I couldn't find something with no development, and they couldn't. I don't take credit for anything. But the statement was, oh yeah, well, people have thought about that some before, but you know, the materials will never take it. You're talking 600-700 dPa, that's just nonsense. Material known to man, one of the materials guys, fuel guys said, can handle that. But that didn't deter us, though. We just went to work to find out if there are ways to reduce the requirement of the materials and to advance the materials themselves. And so all of the benefits seemed intact if we could solve or benchmark or determine the limits on certain key things. And so now it's a fairly efficient global effort. There's one group there's 105 of us all together up in Bellevue, Washington, and some 3/4 of them are technical types, working away, and we have convinced the government that it's a good goal to have, that if you can have a reactor which requires little or no enrichment and not much reprocessing, then it's a good thing to export. And so the State Department went to bat for us, and they have negotiated agreements with other countries so that we can openly talk about the reactor design. Can't talk about enrichment, can't talk about reprocessing, but if you can make a system that simple procurement, where a country can guarantee some energy security just by buying a reactor and some cheap fuel, depleted uranium, for example, then that's a good thing. And so my next advice is be a little bit stupid like I was, because had I known then it would take us 3 years to get the governments to get all these agreements signed, I might have said, skip it. We just kept going. And so now we do have permission more and more to do open exchanges with these other countries and to work together, actually. It's efficient because there is still this central control. There's a desire on the part of the partners to form a very efficient organization that will have authority and money and the ability to work around. Because on any first of a kind thing, bad things happen, and you just solve it. If you start a project that's a whole new kind of reactor and you don't have any problems in developing it, something's wrong. It wasn't that advanced after all. There were a lot of limited people before you, and no, there were a lot of smart people before me. So we have most of the national labs involved in one way or another. We pay them. That's a culture shock, that the money going the other way around. And universities, such as yours, we have 10 or 20 companies working for us. We have the Bechtels and the Chicago Bridge and Iron starting to help us out. And the list goes on. So there's, if you look at the globe, there are dots all over it right now. But unlike some projects, we run it in a very tough love way. If you're doing well, you continue. If you're not, we think again, we move stuff around. So my advice to young people is act really sweet, but really be tough. Okay. So now, TerraPower today, I promised to talk a little bit about TerraPower. We have investors from all over the world. Bill's the richest guy, Mukesh is the richest guy in India, I think. Vinod Khosla, other private investors. And some of the larger investors are not shown here because it's an entirely private operation. And if you want to be able to move fast, start out with a few people in a totally private company, because then you don't have to go to stockholder voting except on very major issues. And private companies just have a lot more freedom. And we have not accepted government money. There's a price tag. Everybody's got their price. If the government came in with a huge amount of money, sure, I'd accept it. But don't take on the contractual constraints from the government until you decide it's worth your while. And the ability to act freely and recruit the best possible people is huge if you have a private company. That's one of the reasons we were able to get really good students like you and experienced people from the industry is because we're doing something, and our goal is to build a prototype, not just study it. Every problem we've identified with this, we have a development program associated with it. And another problem arises if it's a killer, we stop. But we don't think there are any. That there are issues to be addressed, pumps to be developed or improved upon, materials to be improved upon. And Bill likes to talk a lot about the digital age and the profound ability we have to model things now, which we didn't before. And some of our young people worked out, Nick Turin, for example, and others did. These programs where you're a single contributor can pull in all the departments, in a sense. It used to be documents going between groups, now, as you know, we just have these wonderful integrated programs. Yes.
What's in these large fast reactor databases? What sort of information?
First of all, of course, how they were designed and run, what metal fuel did they test, and to what displacements per atom did they test that? What safety procedures did they use when they ran their loss of coolant flow test? Exactly what happened? It's lots of stuff. So it's like it's a good physics prototype for what we're designing.
Is the TerraPower reactor a fast reactor?
Yes, it is indeed. It's a fast reactor. Ultimately breeding and burning plutonium. And it went through lots of different versions and forms before. On the upper right was the early work by Teller and Lowellwood. And in essence, what you did is you started out on the left side of that green field of U-238 or depleted uranium, and you started up a breed-burn way moved across. And if you needed to sustain it, you had to be able to breed quite well in order to make enough plutonium for it to be self-sustaining, which meant you couldn't have too much structure in there, and lots of other tricks. And the core had to be pretty big because you counted on a low leakage core, which is a different art form than a high leakage core. And so I won't go into the details today, but we decided not to have the wave move through a solid block of stuff and have cooling systems move with this burn wave. Instead, we decided to move the fuel around, but it's still basic, the same basic idea. And so there's a low leakage, high leakage core, which is more the traditional approach. And then there are all kinds of variations on the theme, including one where we say, well, we'll have a once-through cycle. And let's see here. I'll come back to that in a moment. which if you can learn how to use depleted uranium as your basic fuel, then there are lots of things you don't have to do. And so that red stuff just says what I said before. And I'm willing to talk at length about this afterward. This is a slide that turned on Mr. Gates, because those are the depleted uranium canisters, the Paducah. And there's a lot of energy in that. It turns out if you figure out a way to make depleted uranium your basic fuel after startup, lots of other stuff flows from that. If you design the reactor to do that, and you end up with metal fuel in order to do that, have the right spectrum, you're also getting thermal conductivity. And if you have sodium conductivity as well, if you have a pool type reactor, it just propagates down to where you get a lot of stuff for the ride. Once you've said, I know how to use DIID as a fuel. It's not the only way to go, it's just the way we found in 2007 to do things. And he took a look at that field and said, I'm in. But of course, there was a lot of technical discussion before that. So there are, some people would say it this way, the new regime of safety standards, the idea you don't need on and off-site power to keep the place safe, avoid hurting the public, has to be cost competitive. Not having to do things is a good way to reduce cost, but these reactors, we have not yet discovered a reactor that's really cheap. Maybe molten salt guys or something will come up with something that's really seeking to his horn form a little bit. And it's environmentally friendly, you produce a lot less waste. Bear Peterson was saying, well, you guys make so much less volume. In the discussion we had today, that boreholes make sense for you. He's still supporting that, which we're happy for. And then proliferation resistance. If we make a bunch of plutonium, we don't burn it all up. But the guys who make their living are worrying about weapons proliferation, like the idea that we're not taking it out and then have a huge quantity in transit and then reprocessing and then coming back. That's more dangerous for them than saying you keep everything, the whole fuel cycle is basically inside the reactor vessel, and then when you're done after 10 years or 15 years with some of the fuel, you bring in some more DU and you dump the other stuff down the world, and they like that. And each country we've talked to puts different emphasis on the difference of these. So the countries with weapons tend to not worry about proliferation resistance until they start noticing the other countries developing it, and then they start to worry about it. So there's a time phase in these desires. And this, I put this in just for you in the sense that we talked about, perfection is not required. In the far right column, it says that if the fuel structure cladding cannot take 480 dPa displacements per atom, if you can't do that, then you can't continue to run on totally unenriched fuel. You need enough time to pull that off. But if you can only get it to 200 dPa, you still have advantages of efficient use of uranium, safety, environment, proliferation resistance, the SWOs you need, etc., in comparison to the light water reactor. And so we've seen lots of very interesting evidence that if you know how to control the crystalline structure of HD9 Steel, for example, then you know how to increase the radiation resistance of that alloy. And so at some length you can take a look at this later. But in essence, what you're doing is you go from the right to the right, you're using just DU. On the left, you're adding some enrichment in the cases in between. I'd say the uncertain part here, of course, is there are cost advantages up to about 15% relative to the light water reactor. But there's a lot, and we do that by calculating the levelized cost and so forth. And those calculations are as good as the assumptions. What we have not discovered, and what I want this group to invent, is the one that's 25% less. But you get so much stuff that governments care about with this style of reactor, progress on all these fronts. Even in light of imperfection, you need a robust approach with a robust set of possibilities.
What metal is supposed to take these DPA?
It's a HD9. It's gone up to 200, and there are heavy ion screening tests that seem to indicate up into the 400s, but you never really know until you put it in a test reactor and run it. Or you keep the licensing of the machine consistent with whatever DPA you
So
have
it's
achieved.
HD9 steel.
Yeah, and if you ask me a deeper question, I'll have to refer you to the materials experts who know a lot about this stuff. So that's my point. Have robustness to your effort. I'm going to skip down to this, which is once through mode. We're talking now about not reprocessing, but is our main approach. Here's the traditional approach. And what you do is you look over the life of the plant and you ask, what's the school requirement, for example, for the TWR versus the LWR over the life of the plant, cumulative school requirement. And then you look at what we call the advanced mode, once through mode, which is an idea that you and I talked about years ago, Ehud, which is at end of life when all this stuff is starting to wear out. You plan on a core transfer because this guy's working perfectly fine if you plan it right. And this was a really hard idea to sell, by the way, but you take this and you put it in the new one, and you pull out the control rods and you go again. That's a rather oversimplified version. But the point is, once you've started up one of these on enriched uranium, you can continue running essentially forever without the need for an enrichment facility. Boy, did we have a hard time with the practical folks out there making fuel. And one of our leading members of our group ran the fuels business for Siemens and so forth. But they eventually came around and said, well, it's not as easy as you think, it's not as free as you think, but you're right, you don't need enriched uranium to pull this off. You just got to plan on it way ahead. And so that's what we would call our advanced once through mode. Once you've done enough enrichment to start up this thing anyway, you've got enough DU around to run it for centuries. Well, the problem is the plant wears out, so you have to be able to do this core transfer. Pretty neat. Pretty neat. We talk about building a prototype. We're serious about it. We've designed the core and the nuclear island. We know what needs verification. We know the difference between benchmarking and needing to find out how far certain things can go. We could give you a whole nother session on this. This is a 600 megawatt electric plant. And ask why so large? Why don't you build a little bitty one, for heaven's sakes? Well, unfortunately, the one problem that this shares with the fusion program is you need a certain size to make it work. And the neutron economics gets good at about, I forgot how many definitions, but a fairly good size reactor. If you want to see things happen in a finite time, then you better run it at about 600 megawatts electric. We can look at 300, but you can't look at 10 to prove your point. There are other concepts, advanced concepts, that could be looked at in much smaller scale and then scaled up if you want to. But it's a pretty big effort, but it's a very serious effort being taken very seriously by a number of big institutions. I don't know. Let's see what happens if I... How do I make the little arrow go around with this thing? I'm showing my illiteracy. Is there a mouse or a... little pad or something?
Trying to do?
I wanted to click something on this.
That's this little.
Oh, well, see, my finger doesn't work.
Ah,
Just click it and see what happens. Okay. This is just for the fun, but this is called fuel shuffling, and it's the equivalent of moving the fuel rather than the wave. And, you know, when you're done, you take this one that's reached its DPA limit, you move it to the outside, and then you move some stuff that's been cooking up plutonium ore into the middle. And there's a real art. It's taken years of figuring out how to meet all sorts of criteria at once, not just the DPA limit. And in fact, we went from many more hundreds of DPA down to about 480, which is getting us.
Is that shut down when you're shuffling?
Yes, you have to shuffle. And not only would the regulator not let us do it, I wouldn't, which is really saying something.
Is the fuel pellets of UO2 or uranium alloy?
It's uranium and it's metal, and it's
Uranium metal alloyed with what?
it's essentially nothing. It's yeah, and that in itself is interesting. We've run tests on watching sodium react with fuel, metal fuel, and it actually is much better than the oxide because the problems don't propagate into the coolant. And so this down at the bottom talks about developing an execution plan. People are working on things like division of responsibilities, how would you organize a project and all that stuff. But in this country and in other countries, people keep bringing up the AP 1000. Aren't there lessons learned for us there? And there certainly are, although it's a very different kind of effort. This is a development, first of a kind, first of species almost reactor. You handle that differently than a great evolutionary advance like water reactor. But, so we look at the lessons learned from all the other sodium-cooled reactors as well as the AP 1000. But AP 1000 is a popular topic these days. I'm sure you guys get asked about that all the time. This is a something that someone could give you a lecture on sometime. It involves radiation tests and ATR, different types of fuel, the fast spectrum tests in 460, and then finally the prototype. And long-windedly, there's someone coordinating all this stuff and money flowing all around and results flowing all around to finally end up with TWR fuel. And if you don't have a real mean team, you'll never pull it off. But if you're right on top of it all the time, you can make progress, and we have. So we're doing stuff. We now are the proud owners of a couple of tons of HD9 steel that we don't know what to do with, but the point was they had to find out things that would work small will work in industrial quantities. So we're into that phase, and that looks quite good. Idaho National Lab is doing a whole bunch of stuff for us. They're upgrading facilities and doing a prototype fuel fabrication line. And there's other work going on in other parts of the world. And so, one of the things that's impressed one of our potential partners is that we don't do things based on who wants what. We do things based on what a real risk analysis tells us. What is the technical readiness of every single component in this reactor? Where do we have to make progress and exactly what kind? And we bring in independent review and all that sort of stuff, and then we use this technical readiness, it's like another good lecture in itself, analysis to guide us in what we need to be doing. And we stay a small group and try to access the talent and participation of the best people in the world to do whatever piece that is. So we don't want to be a Westinghouse. Westinghouse is a fine organization. We're not one. We want to be an outfit that's very clever about getting the big boys to finally change course and build this, I think, wonderful new type of reactor. So it's a hard-nosed game. So back to my lessons, which I typed up at lunchtime, and maybe they're still right. Technical merit is necessary but not adequate. Be ready. Always know what you want. International collaborations occur when there's a benefit to sharing talent and costs, i.e. it's a very long-range thing. And you'll run into that. It takes a long time because to get things going, so you better be ready to work in parallel for quite a while, continuing to prepare to hone your idea, because governments are full, I found, of really well-meaning people, some of them very smart, but they're working in an infrastructure that, in a collection of institutions. Just think of the number of institutions that have to rule it's okay. For us to do this internationally, we had multi-agency reviews that involved NRC, Defense Department, Treasury, DIII, I've forgotten how many, there's so many. It took a while to do that. And then there's a sort of risk, such as Fukushima came on. That delayed everybody. There's these reassessments going on, etc. Germany's an extreme example where they're trying to make solar power look great where the sun doesn't shine. That's one German executive said to me, that makes about as much sense as raising palm trees in Greenland. Nonetheless, that's the kind of thing you have to watch out for. So if the time scales are long, you need to make yourself robust against regime changes, government changes, whether democracies or not, as well as external events. And when something like Fukushima does happen, really reassess what you're doing. Is there a lesson in it for you or not? And then, based on past experience, make sure there are one or two dominant parties who get together and figure out how to do it. Then invite the other people in if you want to make it multinational. The difficulty of pulling off something that goes up is the fourth power, the number of parties or something. And make it merit-based, have your own version of a technical risk assessment, and have an empowered lead project management team. This sounds like motherhood, but I watched it both ways. And it's all true, and the art form will be to recognize when it is this and when it is that. And so that's what you wonderfully young people will become expert in on an international basis that I never conceived of before. I made it up. That's all I have to say.
Thank you, John. Any questions?
Could you give us kind of a simple step-by-step what needs to happen from today until TBRP is in operations?
What has to happen from today is that a team has to be formed, which is funded to and has the authority to do the rest of the technology development and design. We've taken the design far enough to know it can be done, but we'll find things along the way, problems that need to be addressed and that require that real efficient thing. You will have to have technology development programs in a number of institutions who are focused on your particular problems, and we have that now, but we'll need to continue it for some years. A big step is to get the design to the point that you've done the preliminary safety analysis, and this is approved by the appropriate regulatory body, and that's the long pole in the tent in the sense of uncertainty in the schedule. You may find you have to use a phased approach to the operation of the first device. You need to get the regulatory people in early learning with you. And then there's the first concrete, as they say. That's a big milestone. And you have to have the really big time guys already educated and brought in before that happens. don't wait too long before you do balance a plant, because you think that's the trivial part, but it isn't really, for reasons that you don't spot at first. And then you have to go through the startup of this machine for the first time. And it's a new regime of safety in the good sense, but it's also a new regime in the sense that you're going to be benchmarking all these calculations and things, and this wonderful modeling and all this benchmarking data which you've got, that you have to have against what actually happens. And to me, that's the really interesting phase of the startup of this thing. And then you have lead assemblies in this prototype, which test more advanced forms of fuel appropriate for a commercial unit. The prototype's going to accelerate to a certain degree the testing, and it'll put out a lot of power and generate a lot of electricity, and you get paid for it. But it's there to prove a point. And then come the commercial units. And
When
you have
is
to
that
dis-
scheduled to go on?
Mid-20s.
Mid.
On air. It sounds like a long time, but it isn't, given everything you have to do.
Isn't that true that most of the spent fuel you showed over here are oxide, in form of oxide? Now, if you want to convert them to
We don't.
metallic form,
We don't.
you're going to have the same problems that everybody else has in terms of safety and safeguard.
Well, what we do is we start out with enriched uranium, not anybody else's spent fuel. We start out with enriched uranium at sort of 12 to 15% enrichment is the igniter. It's metal, not oxide. But people know how to make metal fuel. They've done it before, and that's the whole point of this fuel line that's being prototyped. And then what we don't do in this nominal plan is we don't take spent fuel from light water reactors and put it in our reactor. We can, but then we have to metallize it. And then we have to do a lot of other things, and it's very expensive. So our baseline is to use metal fuel through and through, i.e. you take the DU that's in these tanks out there, and you do have to make it into metal fuel, but people know how to do it. And it's
Well, that's uranium hexafluoride, is it not?
correct. And the guys who work for me and run these fuel fabrication facilities say, yeah, the problem is not they don't know how to do it, but there's no industrial scale outfit converting this DU to metal. And there's not a lot of industrial use of metal fuel in the West for metal enriched fuel. So we actually have an outfit setting up the line for us for both those.
How long does the first core last? Does it limited by the DPA or limited by the fuel you put in initially?
Fuel, I'll give you two answers. If the commercial unit we're looking at right now, and in that study, or that design, you make the assumption it's good for the 480 DPA. You'll still take fuel out and put some DU in.
So you have to shuffle new fuel into the core.
Yeah, so you'll take it actually out about every decade or longer. You'll say, okay, it's time to do a major overhaul, and by the way, we're going to take fuel out.
But you
Well,
mentioned
for-
about changing the core into an,
Yeah,
just
that's
take
much
over.
later. That's 60 years. Yeah,
60 years.
60 to 80, you name it. That's when you decide this reactor is too old, and we need to redo the island. We need to do so much stuff it's the end of the plant life. Light water reactors now, they talk about what, up to 80? Is that right? Up to the discussion at least. Well, I don't know.
But the
answer
core
to
never
that.
lasts that long in light water
No.
reactors.
Yeah, well, this core doesn't either, because
Oh.
every 10 years, you take some out and you
Wow.
bring some DU in. If you made this thing such that you didn't have to bring in any fuel, no DU, no nothing, the reactor would be too big. It'd just be very, very expensive and huge. Theoretically, you can bring in enough that it runs forever, but forever is a long time.
So, but you
So
still,
the
after you,
practical world is about every decade, maybe 2 decades. You would take some of the fuel out and bring in not enriched uranium, but depleted uranium, additional fuel, and continue the breeding process.
What do you do with the spent fuel that you take
You
out?
put it in our current version is the borehole,
Oh,
pairs that thing, but our volume of fuel is small enough that we seem to fit that. Yes, sir.
I have a hypothetical question. Your
those are
State
always-
Department has given you permission to talk, and you do, and you talk to foreigners about this. Supposing in one of these discussions with serious partners that might build this for you, or with you, they bring up the idea that you'd like to raise the enrichment a little bit, or maybe even 21%, or they'd like to do a little bit of enrichment. What problems do you have with State Department or whoever U.S. government regulates?
Essentially none, as long as we are on the path of the traveling wave reactor and we're reducing the total enrichment. See, we're not allowed to work on better enrichment methods or internationally better reprocessing methods. But if we say this is a traveling wave and it reduces the amount of enrichment required by a lot, and we don't need reprocessing in any of these cases, then okay, that's good. And the intention of the whole program, of course, is to, and the possibility is high, now that we've got the DPA requirement down to 480, that we'll get there. If you asked me that question 2 years ago, I'd scratch my head and say, he's me guy. But they had not done all of this correlation of crystalline structure to what kind of beating it was able to take in heavy ion simulations, and then they compare it to stuff that actually came from FFTF, that was metal fuel. They'd put it in, and they'd see the correlation they expected. The FFTF stuff didn't work very well. Ours worked multiples better. So all this stuff is going on.
If I may comment to Roshan. So we have some ideas here to how to make use of the fuel that comes out from the TWR core. It has sufficiently high reactivity. Even with most of the fission products retained in the fuel, you can still use it to run PWR.
Yeah, I understand, but what I'm curious to find out is your TWR have a similar back-end problem, like light water reactors. Light water reactor, you also have spent fuel, oxide-based, and somebody actually proposed to put in the deep borehole.
Yeah.
Well, you have a metal fuel. How do you put a metal spent fuel directly into a deep borehole? I mean, the waste form is going to have a problem. So somehow you have to process it. So in the process, you run into the problem of proliferation problem, because you have to break you have to somehow convert your spent fuel. So that's still need to be worked on. But the similar back-end problem apply to your reactor as if any other reactors there.
Well,
The only difference is that the volume utilization in this reactor is more than 1 order of magnitude, and a factor of 20 higher than in light water reactors.
In terms of what? In terms of the material
How
that
much
exists?
energy you can extract?
The reactivity, I mean, the utilization of the reactivity, certainly I can assume you utilize it higher. But you have the same amount of problem in terms of fission product and maybe some unburned or produced plutonium in your metal spent fuel as you've been in light water reactors spent fuel.
so the presumption here has been, and I have to talk to the expert, but since we are not using sodium-wetted fuel, we're not.
Yeah.
Therefore, it's much easier to dispose of directly without intervening processes. If you have sodium-wetted fuel on the inside, that's a different deal.
But ultimately, geological disposal, you need to put into a sufficient, robust waste form. So, in Yucca Mountain, you could not even put metal fuel in there because of all the other chemical reactions. So I assume that you have a similar challenge when you're trying to put it into a deep borehole.
Well, we're told by the experts we don't.
Yeah, I understand. It need to be researched onto it. Yeah, I agree.
He was raising his hand back there.
So you mentioned one of the entering arguments was that it has to be affordable, making the broad assumption that a carbon tax isn't forthcoming in the U.S. anytime soon. Who's going to be your primary customers once you actually have gone through the prototyping phase and have a
Well, the United States could be a great customer eventually, or co-developer, but we're not exactly suffering from lack of energy right now. There are companies, I don't know which prevalent information, but there's U.S. utilities who've taken a look at the potential carbon tax, and have seen that in the 30s they have to convert. There's no choice but nuclear if that continues to hold. China's going to build thousands of reactors. We'd like to see them directed toward the safest possible, most efficient proliferation-resistant scheme. They have plans to export reactors just like the U.S. We'd like to see the most proliferation-resistant scheme we can think of there. And there are a couple other countries we're talking to. Of course, India right now has a nice fast reactor program going, but there are political problems still for doing collaborations with them. I'm not sure I quite answered your question, but it's clear that at some point that there'll be a break in that direction. As I was saying earlier, I think someplace else, if I had one wish that could be granted, it would be we had more education that someone brought up. Everybody says that, and then nobody can figure out how to educate the public because of its tendency to take a conclusion and then, no matter what the evidence, even counter evidence, put it as reinforcement of their conclusion. But the Columbia Earth Institute did these studies of mortality per megawatt hour produced by coal, by gas, by everything else. And it's just stunning, even if you throw in Fukushima and Chernobyl, the nuclear is 1,000 times less hazardous. But there's a real psychological thing that has to go on. So I wish I could see more. It's hard to have a highly educated institution that's also impartial. You guys are all, after proposing your ideas, and they're good, but I wish we could find a way that policymakers could see more stuff like what Columbia and NASA Goddard put out, and I'm sure there are other things. But I was asked that in front of a group in Seattle, a bunch of great dignitaries, and I was tagging along. And they asked what would I really wish for if I could. It wasn't just more international collaboration, it was how to better inform policymakers. And I could have a few Will Rogers remarks about moves in Congress, but I won't make them. I think we're...
Okay, time is running out, so whoever has additional questions...
I'll hang around a little bit if you want.
So let us thank again.